Alright, let's do some more LeetCode. The first LeetCode problem of the day is LeetCode number 210, course schedule 2. Their number of courses, yep, we know that much from course schedule 1. So let's see, course schedule 1. What do I remember about it? It was a topological sorting problem. Basically, you just take the in order, you'd grab the first item that didn't have a prerequisite, and then you just slowly go from there until you'd either hit a cycle in which you couldn't solve the problem, or you ran out of nodes, in which case you did solve the problem and you know the order in which to take the courses. Anyways, let's see. Return the ordering that you should take. Okay, so I think, if I recall correctly, was course ordering or course schedule 1 just whether or not it was possible? And so I guess course scheduling 2 is asking us to actually return this order. Okay, and if it's impossible, return an empty array. Okay. Okay. So let's take a step back and think about this again. So topological sorting, this time with printing the order. So first, create and populate a map int list int, where the key is the course and all items within list int are prerequisites. So this creates in degree or in edges. Then then we would want to say iterate over the map, find the item which has no items within its list, and that is a potential start. To the ordering. Then, so what we probably want to do in that case is that while the map is not empty, we iterate over the map. Then for each item within the map, so this would be O of n, let's say. Then for each item within the map, remove the item if it exists within the, remove the course if it exists within the list. Or we could use a set instead, now that I think about it. Assuming that the courses are unique in integer, then this would be faster than removing from a list. So for each item within the map, remove the course. This course is this course that has no items within its list. Remove the course without in edges, or prereq if it exists within the list. So this would also take O of n time. And then this would continue and repeat until the map is not empty. And then we can also say add the course into some final list. And then if the map if there are no courses which are empty now, then a cycle exists and therefore return an empty array. Otherwise, return the list. So this last check solely exists because of the fact that we're using a while loop, and we need to terminate it somehow if a cycle exists. If a cycle exists within the list, then there will be no courses which have no prerequisites, and thus if there are no courses without any prerequisites, then we know that it is not possible to complete this set of courses, and therefore we should return an empty list. Otherwise, we will eventually hit a point where the map is empty, and therefore we should return the result list, essentially. Of course, assuming that we have n courses, we have to iterate over n courses, then n minus 1, then n minus 2, n minus 3, all the way until one course, right? So this in total, we can say that this inside takes up O of n total, because these are not running nested, these are running in the same sort of layer. So both of them will take O of n time. However, these will take O of n time, but these will run sequentially, so they don't stack. Now this outside one is running O of n, and then n minus 1, n minus 2, like I said. So I'm wondering now whether or not, in total, whether or not this would be running in O of n squared or O of n cubed time. Because if the outside is O of n minus, or if the outside has n minus 1 entries, then the inside will have n minus 1 entries. Let's see. If I had... we had to run through n entries. And inside we had to run through n minus 1, n minus 2, n minus 3, n minus 4. No, that's total. That's aggregate. So I think in this case, I'm leaning towards O of n squared in total, but I'm not sure about this entirely. As for the space, we are also going to be using O of n space, just O of n space, because we will be adding items into this map, and at most this map will have n items. And then when we remove items, we remove them from the map and we add them into our result list. So at most we will have n items no matter what. I think this is a pretty reasonable starting point. Let me think. Because the input size does seem to be a little bit large for this. Because if the input is at most 2,000, and most of the inputs that we've been running before have been like, most of the inputs have been like 100 squared when it comes to O of n squared algorithms. Perhaps this is not fast enough. Let me think. This is the number of courses, right? The prerequisite length. So if we imagine each course Okay, let's actually redo this. So let's do this in terms of a graph problem. Let's actually do this topologically, like with topological sorting, in terms of like the runtime analysis. So we know that this will be O of V time, or rather O of V squared total, because we need to go V, V minus 1, V minus 2, V minus 3, V minus 4. Well, hmm. Not necessarily, actually. We don't need to check all of the items, because if we find an item within here, if we find an item within the list which now has no prerequisites, then we know that that will be the next node or a next node that we can tackle. And therefore, this can be shaved down to O of V time. If we tell the algorithm which node is next without scanning. This, however, will take up O of E time, right? There's no way around this. We need to iterate over all the prerequisites and remove the prerequisite of V to E. We just need to remove all the nodes or all the edges that are coming out from V. And we don't need this. We can say if an item now has no items within its set, we can use that element for the next cycle. The idea is that we choose the next node at that point, as long as it has nothing in its set, and we can just use that. So maybe in this case we don't want to use just a map is not empty. We could also consider using a queue. And then we add the course into the final list. So there and there. And then if there are no courses which are empty now, then a cycle exists and therefore return an empty array. So this will probably be if the map is not empty by the time that the queue is empty. If the map is empty, otherwise empty list. So in this case, then we will be O of V times E, with the space being O of V. So this is a better justification. However, that doesn't really actually get us closer to, that doesn't really change our runtime in general. We're still running into a pretty expensive operation, but is it possible to do better? If we spend a little bit more, space to also track the out edges, if we track the out edges, then how can we use it to save the asymptotic runtime? Well, if we know all the out edges, then we know all the nodes at which we need to delete the edge, or we know all the nodes in which there are in edges where we need to clear that node. So then we would then basically check just the nodes themselves, the nodes that we need. But would that actually cut down on asymptotic runtime? I think I did something similar for course schedule 1 where I had an adjacency list for in nodes, for in edges, and then an adjacency list for out edges. And that might be the play here. But would that necessarily be a better? Would that help us asymptotically? That's what I'm wondering now. Well, it really depends on how many edges a node has on average. Mainly help if the number edges on average is much lower than the number of nodes. And since the number of edges is at most number of nodes minus if we're talking about directed, times 2, right? It's a number of nodes times 2 because each direction minus 1. Or is it like this? Number of nodes minus 1 times 2? Because for each node can have n minus 1 edges to each other node. So we have v nodes, or yeah, we have a certain number of nodes, and if each then in that case, wouldn't it be nodes minus 1 squared? Let's see. No, not really. But the number of nodes, or the number of edges, will usually, or can be larger than the number of nodes. I feel like there's probably a mathematical way to prove this, whether or not it will actually improve the runtime. I think my mind is just blanking on that proof. I understand that for the number of I think it's the other way around, where it's the number of vertices is equal to some multiple of, or is at most some multiple of the edges Could be wrong there too. But in any case, I'm not sure if this will actually help us. I think the topological sorting with the in degrees is as much as we need. I don't think this will help us asymptotically. I'm going to go ahead and start coding it, and then we'll see if it's actually fast enough. If it's not fast enough, then we'll have to think of something else. So let's start by creating an in degree is a mutable map of integer mutable set of integers. And then we can say for num courses for each. Or rather, what we can do is prerequisites dot for each pair in degree get or put into pair. So for example, in order to take course 1, you have to finish course 0. Ooh, sorry. Chair cover. In order to take course 1, you have to take course 0. So in degree, we want this to be the first get or put pair 0. We want just a mutable set of int. And in degree dot, or rather, val list is equal to u as mutable set of int and set add pair 1. So we add the prerequisite into here, into the set of items, and then we can say print line in degree, and then we can take a look at what this looks like, right? Oh, this should be a mutable map of empty array of int. Oh. Is there an empty int array? Or am I going to have to do int array size 0? Okay, yeah, so for class 1, you need to get class 0. Let's see. Because we want to produce a set for all of them, right? So then we want to say val, if in degree get pair 1 is equal to null, in degree dot put into pair 1 just an empty set of type int. Because we just want this here in order to basically have or null mutable set of, and this should just be get. Just returns null no matter what. We want to have a full set in order to know which actual course to start off with, right? And then we can say val q is a mutable list, or we can say a linked list of integers, and we can say prerequisites for each, or not prerequisites, in degree entry if entry.value is empty, q.add entry.key. And then now that adds all the, so this adds all items which have no in degree. And while q is empty, we just negate that. Then we can say val front is equal to q.poll. And then we can say in degree for each entry again. If entry contains front, entry remove front. If entry.value is empty now, then q.add entry.key. And then afterwards, we want to say in degree dot remove key or front. We could do that first, right? And then we can say we want a return list, right? So return array is equal to an int array. What size should it be? Well, it should be the size of our nums, right? Our num courses. And then we can say return array at, we want a counter, right? So var counter is equal to 0. At counter plus plus is equal to front. So this will just keep on counting up, which is what we want, because then we're just sorting, basically. We're just putting in the course that we want. And then here we can say return if in degree is empty. We want to return our return array. Otherwise, return an empty int array. So this counts up and adds the new item into our list. And let's see, contains entry.value contains. And this should be entry.value.remove. So entry.value is the actual set within the entry. Okay, cool. And then we know that works for the first example. Let's run it for the other examples. Looks like we hit an out of bounds. Let's see. Start at 0. Let's see. If we have num courses, then we should probably do num courses plus 1. Because if we have num courses, if we have 0 to num courses minus 1, well, this starts at 0. And theoretically, this counter goes all the way up to num courses. Okay, so we had to go num courses plus 1 then, I think, in order to avoid the out of bounds. We could also use a list and turn it into an array. Okay, so that doesn't seem like it's working out well. Let's see. Interesting. That didn't really fix the problem. Kind of made it worse, honestly. Let's do print line and let's say front, and let's see what's going on there. So the first one should be 0, then it should be 2, then 1, then 3. Let's see. 0. Let's see. 1 depends on 0. 2 also depends on 0. So when 0 gets removed, then we add 1 and 2 into our list. I see. And then we remove 2 again from our list, or we add 2 into our list. In that case, what we want to do actually is remove it as soon as we add it into our queue, so we don't go over it again. This might yell at us for concurrent modification, though. In which case we're gonna have to do something different. Actually, I'm like pretty much 100% sure that this is gonna yell at us for concurrent modification. In that case, we're gonna need to do, let's see, for yeah, let's see, entry as or in degree. So you use a for each loop. This shouldn't yell at us because it doesn't care much for concurrent modification. So now we should be able to remove that value from in degree without much trouble. So the idea is that once we add it into our queue, we don't want to pick it up anywhere else in any other iterations. So now we should be getting what we want. Still okay. In that case, if we didn't want to remove it like so, how else could we handle it? Because the map is not sequential, so we can't use just the standard indexing loop. Well, I mean, there's no reason that we can't. If we had an array of list mutable list int of size num courses, then rather than setting or putting, or this should be mutable set, and then our set is equal to in degree get at hair 0. Val set is equal to that, and then set add. I don't trust that the compiler is smart enough to cast it, so we'll cast it manually. Then here we can say for index in 0 to num courses -1, and we can say if in degree at index contains front, then in degree at index remove front. And if in degree at index is empty now, after that, then add the index, and in degree remove, or not remove, we don't need to remove it then in that case. Well, but then if we do that, then how do we know if we've already established, how do we know if we've gone over it? We need a set essentially of seeing, of what we've seen so far. Well, we could have this as a set, and since the set obeys the insertion order, of int, return set add front. So if we add this return set, if it contains front, if it is empty, and return set contains, or does not contain rather, our index, and this return set should automatically add return set add entry.key to int array. So now what we do is that we have a return set, and since the set will obey the insertion order, we should be able to convert it into an int array. If it's a stack, then we'll have to reverse it. If it's which will cost some time, which will be annoying. So hopefully it doesn't. We could also create another auxiliary data set or return list, though that really won't do much. And then we have our queue still. We've converted this to an array so that we can modify it concurrently without Kotlin screaming at us. So we grab the front item. We'll add it to our return array. This should be return set now. And we go through each index within our courses. If it contains the item that we're at, then we will remove it. And if it's now empty and it does contain our index, and we haven't added it into our queue yet, then we'll add it there. And our return set add front, then we don't need to do this here because we will do it at insertion time. Same here within our return set. So once we add it into our queue, we consider it added to our result. You can remove that. That was just boilerplate that existed so that we could remember what we wanted. So essentially we add it to our queue once it's empty and we haven't added it into our return set yet. We add it to our queue to process next, and we also add it to our return set, and we consider it as part of our answer at that point. So let's go ahead and run this again. And we just add mutable set of int. We need to initialize those values to an empty set. oh, this needs to be a mutable set of. This doesn't. In degree for each entry. This should be indexed now. So these need to add the index, not the entry. The entry is the set. Yeah. So that was the main bottleneck. To int array just, huh. Oh, not in degree. If, That's true. How do we determine whether or not, oh, if return set dot size is equal to num courses, right? Because then we've added all the courses, otherwise we haven't, and we just return. Oh shoot, I gotta take care of something, I'll be right back. I'm not sure why this is not working. If return set dot size is equal to num courses, then we do that to int array. Print line. This return set should be return set dot add. We added that. We know 0 was initially empty. Then we added 0 into here, our front. Then we know that the in degree contained 0, so we remove it. And now it should be empty. And it doesn't, and the return set does not contain 1. So we should have added 1 to our queue and then also added it to our return set. It would be nice if we actually added our index into our return set and not our front. There you go. So that takes care of that. But this is still not necessarily optimal. Like I said, we could probably cut down on the amount of time that it takes. Because this would be going through O of V time. Right? And we know that E is bounded by this. V is bounded by this. Just thinking. This doesn't feel fast enough. I guess that's the main thing. It just doesn't feel fast enough. But who knows? I'm really not sure. We'll see. If it's not fast enough, then maybe this out degree might help. Yeah, it's nowhere near fast enough. If I added the out degree, and the memory usage is already pretty high. Let's see. We'll call this in set. outset. This could be a mutable list. And this should be as mutable set or mutable list int, and outset add pair 0. Actually, what does this in_degree do? This in_degree says that for this particular integer, I have this incoming edge. And so I want to basically do the opposite of that and use that outset. Okay. And now I want to say for index, or rather for each out degree, for each at front, for each course, in degree at index, remove front. We know that it will contain our front item. And then we can say if in degree at index is empty and not return set contains course, then we can queue add index, return set add index. Sorry, course. So now we don't iterate through all the nodes every time, except in the case where the node itself actually contains all of the elements. This should be a mutable list, because we don't need this to be a set. We can have this as a list. We can just add the items there. And so this should, on average, assuming that the average degree of a node going outwards is not very high, then this should be faster. If the number of edges, or if the number of outgoing edges is higher, then or is at its maximum, then it'll be about the same. But on average, this should be faster. Probably not wildly faster, but still faster. So yeah, that brought us down to the average runtime, which I'm pretty happy about, and I think I'm going to leave it there because this video is starting to get a little bit long. Definitely we'll have to take a look at if there's an even faster way of handling this. But yeah, so this is just, again, topological sorting, using the outgoing edges and incoming edges in order to build a more optimal solution in this case. And then we basically just check to see if there's any nodes that have an incoming edges or no incoming edges. We add that to a queue, and then we just continue emptying that queue and adding new edges until we either finish and all of our nodes are within our returning set, or it is not, and in that case we just return an empty array. In any case, I hope you learned something, and I'll see you for the next problem.